All right, so this is our second video on valence bond theory or hybridization. In the first video, I kind of gave you the overview of how it all works. Most students really have a hard time initially getting the picture, but once we work a few examples, I think it'll start to fall into place. So our next example we're going to do is sulfur hexafluoride. I drew the little dot structure over here. Sulfur has 6 fluorines around it. All the fluorines have 3 lone pairs. Sulfur does not have a lone pair. Okay? So if I'm going to do anything with valence bond theory here, I do need to figure out how many groups around the sulfur atom, whatever the steric number is. If I look at sulfur, since there are 6 single bonds to fluorine, that means the steric number equals 6. Okay, so that's a key piece of information. That's going to help me get going on this process. Okay, now a schematic like this could be on your test coming up over this material, so make sure that you can draw this if asked. But I start out and I want to compare the orbitals that sulfur has when it's by itself to how it has the orbitals when it makes this molecule. Okay, so sulfur, it's in the 3rd row of the periodic table, which means its valence electrons are in the 3rd shell. So I'm going to go ahead and say it has a 3s orbital, it has some 3p orbitals, and it has some 3d orbitals. Now, sometimes people look at that and say, well, wait, sulfur is in the 3rd row, it uses its s orbitals, it uses its p orbitals, but we haven't really gotten to the d orbitals yet. So why am I showing the d orbitals? And the answer to that is, when you start the 3rd shell, at that point, all the orbitals in the 3rd shell are available. So it's kind of like if you open a can of Pringles, you may or may not eat the whole can, but regardless, once you open the lid, you can get them all if you want to, okay? And of course, we all know that we would, because who can stop? Anyway, so I've got all these orbitals to choose from, okay? My steric number tells me how many of those orbitals I'm actually going to use. The steric number is 6. So I'm going to use the s orbital, that's 1. P1, P2, P3, I'm going to use all those, so I'm up to 4 now, 1 plus 3. And then I need to use 2 more of my d's. So I'm going to use s, 3 of the p orbitals, and 2 of the d orbitals. That's going to get me the 6 orbitals that I need to use to make this molecule. Now, what happens? Well, we're going to throw all those orbitals in a pot, we're going to mix them all together, and when they come out, the hybrid orbitals are going to be the average of those orbitals. There's going to be 6 of them that are equal. They're going to be in between the energy levels of those. The shape will be in between what they all look like. It's going to be 6 hybrids. 1, 2, 3, 4, 5, 6. The extra orbitals out here, they're still there. So I'm going to put them up here. 1, 2, 3. Those are my extra 3D orbitals. Those are unhybridized. Now, in this problem, they're not going to be important, but we will do problems later where the unhybridized orbitals are very important, specifically when I make double bonds and triple bonds. This is the orbitals, or these are the orbitals I'm going to use to make that happen. All right, so I took 6 orbitals, I put them over here, so now let's talk about electrons. Sulfur in this molecule, and normally sulfur always has 6 dots around it. Now, if I have a formal charge, that can change it, okay? But this sulfur is normal and neutral. It has 6 dots around it. So in a sulfur atom, the configuration 1, 2, 3, 4, 5, 6, that's how sulfur would normally arrange its electrons if it were by itself. But once it makes this molecule, it's going to put the 6 electrons in each of these orbitals. 1, 2, 3, 4, 5, 6. Now I have 6 orbitals that all have 1 electron each. They're ready to make a bond. I can put them in any shape I want, and if there's 6 orbitals, I'm going to spread them out into an octahedral arrangement. That's the shape that I get when I have 6 groups. That's the electron geometry. Now, last thing, I didn't name these orbitals. The name comes from what I used. I used an S, so I put an S. I used all 3 of the p orbitals, not the shell, but how many. I used 3 of them. So it's going to be sp3, and then I used 2 of the d orbitals. So d2. That's the hybridization. That's how many orbitals and which orbitals I had to use. So if on a test I asked you, in this molecule, what's the hybridization of sulfur? The answer, you don't have to draw all this out. If the steric number is 6, that means it's S, P1, P2, P3, D1, D2. So it'd be sp3, D2. That's the hybridization. So that's a very simple, quick question I could ask. I also might ask you to draw all this out. Say, draw the atomic orbitals, draw the hybrid orbitals, fill in the electrons. Okay? Now, any of the hybrid orbitals that have 1 electron in them, those are all going to be pointing at another atom, and they're going to make a sigma bond, which means direct overlap between the center atom and the outer atom. The overlap in between them, that's a sigma bond. So all of these are going to form sigma bonds to the 6 fluorine atoms. So sigma, 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 all the way around in an octahedral arrangement. Okay, so now let's move on to another one. Let's do, if I change SF6 to SF4, the drawing pretty much stays the same, other than now I have a lone pair on my sulfur. So for SF4, again, atomic orbitals of sulfur. I hybridize. So that's like mixing them together, and then I get my hybrid orbitals. So what's my steric number? Well, SF4, there's 4 fluorines plus the lone pair, so the steric number is 5. If the steric number is 5, okay, I got to draw my atomic orbitals. It's the 3s, the 3p's, and the 3d's. That's just, I know sulfur's in the 3rd shell, so those are the orbitals I get. My hybrids, this time I only take 5 orbitals. 1, 2, 3, 4, 5. So if I take those, this time my hybridization, 5 equivalent orbitals, 1, 2, 3, 4, 5. The name, I took 1 s orbital, I took 3 p orbitals, and I took 1 d orbital, so sp3d. Again, if I ask you what's the hybridization of sulfur, you just say that. That's all you have to say. Now I have 4 more orbitals left over. 1, 2, 3, 4. Those are my extra 3d orbitals. They're not hybridized. They weren't part of the redistribution. Now, electron-wise, sulfur has 6 electrons. So if I fill them in, I could show it over there, but really this is the important part here. 6 electrons, 1, 2, 3, 4, 5. I put 1 in each hybrid. If I have a lone pair, because again, my Lewis dot structure has to guide me in filling this stuff out. I have 6 dots. I've only put 5 electrons in. If I want to make a lone pair, I'm going to put the 6th one right there. That orbital, those 2 electrons, that's going to be a lone pair. Remember, that orbital is full now. It can only hold 2 electrons, so it's not going to make a bond. But then the other 4 are going to make sigma bonds. Okay, so my hybridization scheme should show me if I have any lone pairs. It should show me all the single bonds are sigma bonds. And then in my next example we do, if I'm going to make any pi bonds, which are the second bond of a double bond, those electrons are going to go up here. We haven't seen that yet because none of my examples have had any double bonds yet. Okay, but we're about to get to that. So in my hybrid orbitals, I should see whatever lone pairs and single bonds I have over there, they should be obviously shown here. And if I ask you to label the orbitals, they're sp3ds, this is a lone pair, those are sigma bonds, all that needs to be labeled on your schematic. So now let's go on to another. draw the Lewis dot structure of H2CO. H2CO. So hopefully you drew a carbon with a double bond to oxygen, 2 lone pairs on the oxygens, and then the 2 hydrogens. So again, if I'm talking about valence bond theory, the steric number, for carbon, there are 3 groups. Single bonded hydrogen, and the double bond counts as 1 more group. So that's a total of 3 groups. My center atom's carbon, so I would draw the atomic orbitals of carbon. I would draw my hybrid orbitals of carbon. So carbon has a 2s orbital and a set of 2p's. When I hybridize, my steric number 3 tells me how many of these to use. I need to use 3 of them. I always have to take the s orbital, that's the first one, and I'm going to take 2 of the p orbitals. So I'm going to take those 3 orbitals. So you should already at this point know, steric number is 3, I should be taking a s, a p, and a p. That's sp2. I'm going to have 3 equivalent orbitals, 1, 2, 3. I use an s and 2 of the p's, so that's sp2 hybrids. That leaves 1 orbital left alone up here by itself. It's a 2p orbital. It is unhybridized. So basically I haven't moved that one. I haven't changed it in any way. All right? So what happens now? Carbon has 4 dots. I have to put the 4 electrons in. 1, 2, 3. But now I need to make a decision. If I put the 4th electron in one of these orbitals, it's going to cause a pair up. And I'm going to show it. If I put an electron there, that's going to mean that orbital's full. If I do that, carbon will have a lone pair. If I look at my structure, carbon shouldn't have a lone pair if I drew my structure correctly, which this is the right structure. So what that means is I can't put that electron right there. I need to find somewhere else to put it. So where I'm going to put it is I'm going to bump it up. There's a little bit of an energy gap here, but I'm going to bump it up here to put it in that unhybridized orbital. That's going to end up causing me to form a double bond. So now let's talk a little about why that happens. So the first 3 orbitals I use, they're the ones that form the hybrids. Those 3 are going to spread out into a shape. 3 orbitals spread out into a symmetrical shape. That's going to be trigonal planar. So these are going to be trigonal planar. Now, getting into a little bit of visualization, a little bit of geometry and math. So follow this the best you can, but don't get too wrapped up in it. But my p orbitals, if we remember when we learned about p orbitals, we could orient the 3 of them on the axes. We'd have a p orbital laid on the x-axis, another one on the y-axis, and another one on the z-axis. So whichever 2 I picked, let's just say it's the px and py, when I form the trigonal planar shape, if I use the px and py orbitals, the s orbital is a sphere, so it doesn't really have any direction to it. But the px and py, they are directional orbitals. If I use the x and the y, 2 lines form a plane. That's the plane that the triangle forms in. So this is going to be a trigonal set of orbitals in the xy plane. Now, what that means is the other orbital is the pz orbital. Well, if I know the xy plane is flat, the pz orbital is going to be perpendicular to that. So my triangular structure is in the xy plane. That's going to be this double bond. One of those bonds is a sigma bond. I can form a direct overlap between carbon and oxygen. I can form 1 bond straight in between. but I can't put both bonds in the same place. So I'll get into that in the next video, but one bond forms there, the sigma bond here, the sigma bond there, the sigma bond there. The double bond has to form outside of that plane. So if the trigonal planar is then flat, that carbon atom has a pz orbital that's vertical. If I analyze the oxygen, it also has a pz orbital that's vertical. And what happens is, to form the double bond, the sigma bond straight between the carbon and the oxygen is like they reach out and they do a strong handshake. That's the strongest kind of bond when we overlap directly between two atoms. The strongest interaction two people can have with one touch is a good firm handshake. If we want more interaction, if we try to put more electrons in the same region, that region of space is already full, there's too much going on, we have to make the double bond somewhere else. So what happens is the pz orbital over the top is like reaching up and tagging high five with the oxygen atom coming that way. So we have a sigma bond between the atoms. We have a high five going above. That's another interaction, but it's not quite as strong as the sigma bond. So it's an indirect overlap between the two atoms. That's what a pi bond is. Now remember, p orbitals go up and down. So actually, to make a pi bond, I got the sigma bond in the middle. A pi bond, I would make a high five on top, but then we'd also be playing footsies underneath. Above and below that interaction like that, that's going to form the second bond between the carbon and the oxygen. So a double bond is always a sigma bond and a pi bond between two atoms. Okay, I'm going to have to cut off the video for now. We'll pick this back up on part 3.